Swayam Prabha. Digital India. Educated India.
What we are trying to show here is an application of route stability criteria to actual flight dynamics problem, trying to derive some analytical criteria for instability. So this work was done by Phillips. So what he wants to do is he wants to find stability analytical formula for stability criteria, right, using Rouse's criteria for stability. So what he assumes is aircraft is rolling, aircraft is in steady roll maneuver. So here rates are not 0, like the case that we have seen earlier. So rates are involved here, and the equations of motion are coupled. So you start with a 6 degree of freedom equations of motion, and after making some more assumptions. So for example, now what you will do is you will take this aircraft equations of motion and then linearize the equations, right. And afterwards he made some assumptions. So one is this steady rolling roulette is constant, and this is not small because we are talking about steady roll maneuver. So this P naught is not small, but P naught is constant, so that P dot is 0. B, this inertia term, which is cross inertia term, is small and can be neglected. C, flight velocity is constant. Okay. He further assumes that the damping terms are 0 and some other terms as well. So CMQ is 0. Interestingly, he drops this equation so that you will not see the rolling moment coefficients. So the whole objective of doing this exercise is to only show you the usefulness of Rouse's criteria. So we don't go into details of this. Right. So now he defines the two frequencies corresponding to short period modes and the Dutch roll mode in terms of whatever parameter is parameters are left now. Okay. So, omega n sp short period mode frequency, Dutch roll mode frequency is given by so this I y1 is I y over q s c bar. Okay. This q is the dynamic pressure. All right. So, after dropping couple of equations, for example, I think he dropped this Rowlett equation, and he also drops the V equation. Okay. So, we have 6 equations here, excluding the phi dot and theta dot equations, 6 equations here in terms of 3 velocities, right, and 3 rates, and from there he drops the first equation corresponding to this velocity, right, and this velocity is the u velocity, or if you write the equations in the wind axis fixed system, then it is v dot, right, and this equations, 2 equations actually he drops, and he formulates an eigenvalue problem, which is after linearizing the equations of motion around the equilibrium state, which is given by this P naught H constant. So, this eigenvalue problem is this. So, this lambda is the eigenvalue. Okay, let me read what I have written here. M1 P naught, this M1 is some non-dimensionalized mass. Each of these terms which you do not recognize, they are written in terms of aircraft parameters that you know. So, this particular example is from Bandhu Pamadi's book. If you want to know more details on this, you can look into the book. Okay, so this matrix is consisting of lambda, 4 lambdas, right, 1, 2, 3 and 4. So, we are going to end up with a quartic equation in lambda. So, you want me to read this? So, m1 p naught is the steady roll rate, cy beta minus m1 into lambda 0 minus m1 cz alpha minus m1 lambda minus m1 p naught, m1 0 cm alpha 0 cmq c1 minus I y1 lambda minus p naught ix1 minus iz1 0 cn beta minus I y1 prime minus I x1 prime into p naught cnr into b1 minus I z1 prime into lambda. Okay. So, what we are going to see is I am going to see a characteristic equation which is looking something like this. Right. So, there is a quartic equation in lambda, and now we want to use the Raoult's criteria. So, he actually uses the necessary condition only, which says that all the coefficients must be of the same sign, right, in this equation. So, it turns out that A, B, C and D are all positive. Okay. So, for stability automatically E should also be positive. And E less than 0 means we are going to have one or more roots of or the eigenvalues of this equation, right, with positive real part. But for that you need to also carry out the sufficient condition, creating the Raoult's array and then looking at the sign of the elements in the first column of the Raoult's table. So, we just need to look at what this E is. Okay, we do not have to really bother about other 4 coefficients. Let us look at what E is. This is what E is in terms of the aircraft parameters. I y1, which is I y over q s into c bar, I z1 prime, which is, yeah, I have written it there, into m1 squared. This m1 is Okay. So, now use this criteria for instability or stability, right. Stability criteria is that E should be positive and for instability E should be less than 0, right. So, there are two conditions now. The condition 1 for instability, so one of these terms should be negative, right. So, one should be positive, the other one should be negative. Condition 1 is right. So, this is condition 1 and condition 2 these are two conditions for instability. And you look at the parameters that are involved. Parameters involved are inertia terms and the frequencies of short period mode and the Dutch roll mode, right. Rolling maneuver is considered to be a fast maneuver, okay. And the instabilities are also are due to mainly inertia coupling terms. So, this we have talked about previously. Whenever you have an aircraft which is fuselage heavy, I mean all the masses are concentrated towards the fuselage, there you will have instability because of the inertia terms, okay. So, rightly he arrived at an expression which is related to the inertia of the aircraft, and he found some stability boundaries using this criteria, right. So, what we have done is we have used Raoult's necessary condition for stability and trying to find out the stability boundaries in terms of these parameters. So, this boundary is defined in terms of this ratio, of short period frequency over the steady roll rate squared and Dutch roll frequency over steady roll rate squared of that, and using the conditions that we have based on the inertia terms and these frequencies. Right. So, now you go back and look at those conditions and you will find out that in this particular maneuver, the roll rate, steady rolling maneuver, this is the region where you can have stable flying condition. Okay. This region is also stable. So, region 1 and 2 are stable regions. 3 and 4 are unstable flight regimes. And here you will see what is known as pitch divergence. In this region 4, you see what is known as yaw divergence. Okay. So, this is the point which separates out whether you are going to see yaw divergence or the pitch divergence, right. So, if you draw a line through this region 1 and passing through this critical point. So, passing through the critical points which is lying on the boundary of the two divergent regions. If you look at any other line, they are passing through these divergent regions, right, and this line is indicating increasing roll rate. So, starting from here 0 roll rate, in this region the flight is maneuver is stable. If you are passing through this, then you are going to see in this part pitch divergence, in this part you are going to see yaw divergence, right, and again in this part where the roll rate is quite high is stable, but under some conditions. Okay. So, he could actually infer a lot of things just by using the Rouse stability criteria in terms of aircraft parameters, right. So, this is one of the famous examples of use of Rouse criteria to flight dynamics problems. Okay. So, we are starting a new chapter today. So, next 3 lectures will be on this chapter. Aircraft responds to various inputs, right, and so some inputs can be inputs which are unknown, right, some inputs are known, right. What are unknown inputs? atmospheric inputs, right. Many times you will not have any idea about what kind of wind inputs you are going to see. And at times also the pilot input, right, because each one of us will have different reflex systems, right, the way we respond or the way we move our muscles, it will vary from pilot to pilot, isn't it. So that can also come under this category. We will not have an exact idea of what kind of inputs actually can come from the pilot himself. So, but we do not worry about that right now, we take the atmospheric inputs as known inputs, and known inputs are the control inputs, right. So now if I know what kind of input I am going to give to my control surfaces, for example, step input, or you can move your control surfaces in step, ramp, or you can give a pulse, doublet, and so on. And we want to look at how the aircraft is going to respond to those inputs. So the first case that I am going to take is of the rolling motion, and this we have discussed in detail. So if you look at the roll motion of aircraft, the equation for the pure rolling motion is given by delta p dot. No, this is a linearized equation, okay. So about the flying condition that we have, cruise condition, from that we give an alarm input, right, so that we can get into roll. Right. This is from a cruise now. What we are looking at is the aircraft response in roll to aileron input, right, and this input is not 0. So we are not talking about free response anymore, right, we are talking about the forced response, okay. How do you solve this? So one of the popular techniques to solve such linear equations of motion is Laplace technique, right. So you can use Laplace transform technique here. It works only for the linear systems, right. There is a linear system. So if you have any signal, just any signal ft, which is defined for t greater than 0, then you can find the Laplace transform of that, right, which is written as f of s, right. S is a complex quantity. Right. Now use this, apply it here, and you will find there are standard tables given in terms of what signal corresponding to what signal, what Laplace form you can get. A table is given, it is also easy to find the Laplace transform using this integral, it is not so difficult. So let me write down this equation in terms of Laplace form of this equation. And this you can do only when this delta p is starting from 0 initial condition. Okay. Which will have in our case, right, we are looking at roll dynamics starting from a level cruise condition, right. So P is 0 there and delta P is definitely 0, right. Delta P is the disturbance in P. So S minus LP into delta P S equal to L delta A. So relation between the roll rate and the run deflection in S domain is right. This from this equation, this is d delta P over dt. Now you can use this formula to convert it to Laplace form, right. So for 0 initial conditions, so delta P 0 is 0, this is what you will get. Okay. What I want to know is the response with respect to Aeron input. What kind of input? We can take any input, right, any form. Let us assume that this delta delta A is a step input. Okay. And let us say this is the amplitude of the step input. Right. So the function can be written in this form. Now I want to find out the Laplace transform of this signal as well, right. So that I can write everything in terms of S. Now you can again use this to find out the corresponding function in the S domain, and you will find that for this function is A over S. Okay, so what I am interested in is finding out what is the variation of this delta p in time. Right. So you can use partial fraction method and split this into two parts, and now what you do is you take a inverse Laplace, right. So inverse Laplace of this returns you the original signal, right. So first of all what we did, we took a Laplace of the signal, we found this function f in S domain. Later on we can take inverse Laplace of that function and find out what this original signal is. This is one of the easiest method of solving a linear differential equation wherever you can use this. So now if I do that, I can find out what delta p is in terms of time. So clearly it depends upon this LP. LP also gives us the time constant, right, and time constant we have defined to be this. LP is usually negative, LP is negative, okay. So the time constant is positive. So what it tells me is, in the steady state delta p is going to approach some value which is not 0, isn't it, for the unit step deflection in L1, not unit step, the amplitude of this step input in L1, the amplitude is A, right. So this will become 0, right, when t goes to infinity, and what you have is this. right. What is L delta A? L is Q S into rolling moment coefficient into span of the wing, and how we get L delta is this. Where delta A is in radians, okay, because I am writing this as a non-dimensional unit, right. So, delta A here is in radian. LP is now P has a unit which involves second. So, I have to somehow non-dimensionalize this, and we have done that earlier. This CLP has no unit, okay. So, whenever you have been given aircraft data, you have to look at if it has unit or not, right. If it has no unit, then you have to take care of this part. So, this steady roll rate in terms of the coefficients is given as this. And many times you will size your aileron based on delta P SS into 2 U naught over B. So, aileron is supposed to give you roll rate, and you will size your aileron in by looking at this parameter. It's I think it's roughly of the order of 0.07 to 0.09. Okay. Now, let us do an example problem. What you have to remember is, when we are talking about this delta P in time, the time response of the roll rate, then you have to find out this LP and not the CLP, right. That what this formula is for, actually the steady roll rate, right. If I want you to if you want to find how this delta P varies in time, then you also have to find out what this LP is. So, let us look at one example problem, and this is for the aircraft F104A. What we want to find out is the roll response to a 5-degree step change in aileron deflection. Trim speed is given. There is a solved example in Nelson. What other things are given? There is CLP is minus 0.285, CL delta A is 0.039, S is 18 meter squared and B is 6.7 meter, and Ix is 4676. So, A is 5 degrees, right? A is the amplitude of the step input in aileron. So, A is 5 degrees, which is 5 into pi over 180 radians, and LP you can find out using that formula. Turns out to be minus 1.3 per second. So, delta P SS is 0.31 radian per second using that formula. And so, you know the time constant from here, which is 0.77 seconds. So, this is delta P SS, right, for 5 degree aileron deflection at step, and it's going to, the response is going to converge to the steady state roll rate, right. So, this is how roughly it will look like. Right. Any question? So, we can stop if you do not have any question.